I welcome everyone to the ARC Future Timber Hub Research Showcase. Today it's the University of Canterbury Showcase, and this is number 4 of 5 in the series. So as you can see, we've got 5 presentations. So we've had the University of Queensland Structures and Architecture Showcase, the Queensland Department of Agriculture and Fisheries Showcase, the Griffith University Showcase, and tomorrow we've got the University of Queensland Fire Showcase. So my name is Kelly Reichmer. I'm ARC Future Timber Hub Manager and the host today. We also have Dr. Lisa Uttenhouse, who will be chairing the session. She's a lecturer at the University of Queensland School of Civil Engineering, specialising in timber structures. And she is also part of the presentation today as she did her PhD at the University of Canterbury. For questions, please type any questions in the Q&A area on the webinar bar. They will be reviewed and answered during the Q&A time, which will be held at the end of all of the presentations. Please use the chat function on the webinar bar to contact me if you've got any problems listening to the webinar. It is being recorded, so we will be sending out an email out to all participants to let them know when the recording is available to view. It will also be announced on the ARC Future Timber Hub website. And if you require a CPD certificate of attendance, just please email me at timber@civil.uq.edu.au for that. Okay, just a little bit about the ARC Future Timber Hub. It's an Australian Research Council industrial transformation research hub to transform future tall timber buildings. Future Timber Hub is for short. The aim of the hub is to transform the Australian timber construction industry by generating the skills, knowledge and resources that will overcome current technological and social barriers that limit the application of timber to tall structures. And by bringing together a variety of partners, we've got experts from industry, government and academia, the Queensland Government Department of Agriculture and Fisheries, the University of Queensland, the Queensland Fire and Emergency Services, Pine Timber, Arup, Lendlease, Scion, University of Canterbury, Griffith University and the University of British Columbia. So together we formed a unique partnership that spans the entire timber supply chain from primary producer to construction regulator. Our interdisciplinary team includes product manufacturers and scientists, architects and structural engineers, fire safety engineers, and construction managers. The projects also have other partners on the individual projects as well. So I'll now pass on to Lisa, who will introduce the projects.
Right, I'll just introduce the next presentation. So we're leaving Q&A till the end. So the second project was also at the University of Canterbury, and it's actually a fire project. So that one is on resilient design of structural timber beam to column connections in fire conditions. And the presentation will cover emerging questions about the performance of heavy timber constructions in real fires and the need to be able to design heavy timber structures for robust full structure performance over the full fire duration. It will include an overview of the research being undertaken at the University of Canterbury to answer some of those questions and the presentation of recent fire test results. And so that project is being run by Anthony Abu and Paul Horn, and Paul will be presenting, but we have it pre-recorded because Paul is actually running a fire test right now, but he will join us for the Q&A. So just a brief bio for Paul. Paul Horn practiced as a structural engineer, then a fire engineer for 4.5 years at Oracle, where he worked on a wide range of new and existing buildings, including offices, apartments, sports facilities, schools, and hospitals. Seeing many structural fire questions in construction, he decided to investigate a few of these himself. So he's currently a PhD student at the University of Canterbury, researching how seismically resilient heavy timber frame structures perform in real fires. And his research focuses on the response of beam to column connections in fire with a focus on low damage post-tension connections and analyzes the mechanical response of these connections over the full duration of the fire. So I'll play the presentation, and I hope it all works with the sound and everything.
Hello, my name's Paul, and thanks for tuning in to my presentation looking at the research that I'm doing on timber beam column connections in fire. In this presentation, I'll start by briefly discussing what fire exposures to structures look like and what we're concerned with. I'll then give a quick overview of post-tension timber structures, which are the type of structure that my research is primarily focused on. I'll then give you an overview of my research project, and then we'll look at the results from a recent fire test that was conducted 3 days ago. Building codes require that structural elements have fire resistance ratings or fire resistance levels. Let's revise how these ratings are determined for structural elements. A test specimen is constructed in a furnace and is loaded. In this case here, I've shown a floor, but it could be a beam, a column, or a wall, or other type of structural element. The furnace is turned on, and the temperature inside the furnace follows the standard fire curve, which is shown here. This means that the temperature inside the furnace is given by this time temperature relationship. At some time, the structural element will fail, at which time the failure time is noted. In this case, 65 minutes. But to determine the fire resistance rating, the failure time is rounded down to the nearest multiple of 30 minutes. In this case, it would achieve a fire resistance rating of 60 minutes. This figure shows the standard fire in comparison to two real fires. You can see that the real fire given by the orange line heats up quicker and reaches a hotter temperature before decaying, while the yellow fire takes a much longer time to reach its maximum time. In comparison, the standard fire in the blue line is always heating up and does not have a decay phase. But as we've seen, real fires, in comparison to the standard fire, have variable growth phases, decay phases, and durations. Real fires are complex and depend on many parameters, including the compartment, the size of the compartment and the compartment linings, the ventilation to the fire, and the fuel and its locations within the compartment. Therefore, if we want to design structures so that they stand up in real fires, we need to know how structures will perform in the heating phases of fire as well as in the decay phases of fire. The other thing to consider is the structural behavior. The structural behavior of a structural element in the standard fire test is much different to the structural behavior of that same element when exposed to a real building fire. For one, as we've seen, the fire exposures will be different, but the loading and the boundary conditions on the structural member will also be different. Furthermore, there's the question about how the connections perform in a fire and how these affect the global structural response. And we need to know not just how an element performs in a fire, but how the whole system will perform in a fire. So, because the performance in a test is not the same as the performance of a real structure in a real fire. Post-tensioned timber frame structures allow for the construction of large multi-story heavy timber frames. This technology allows for the fast construction of the primary structure because many moment resisting connections can be created in a single stressing operation. In high seismic areas, a low damage lateral load resisting system can be created with energy dissipators that can be easily replaced after an earthquake, and the structure recenters. For cases where the seismic load is much less, this technology can be applied to gravity dominated loadings, which allows for the creation of long spans utilizing deviated tendons. Post-tensioned timber frame utilize a tendon that runs the length of the frame inside the beams and the columns, and dissipators across the beam column interface in high seismic areas. When a seismic action acts on the building, the connections rock and a gap opens, engaging the dissipators to dissipate energy. Because the tendon is tensioned up, it acts to recenter the structure after a seismic event. For structures where seismic actions are much less of a concern and gravity loads dominates, post-tension technology can be used to achieve longer spans utilizing draped tendons, which exert a vertical upwards force counteracting the downwards gravity forces from gravity loads. This type of structure uses a tendon that runs the length of the frame inside the beams and the columns, which is tightened up to provide a compressive force along the axis of the beams and the frames. Then dissipators can be installed either side of the beams, and these are activated when the column rocks. And then there is a shear key, which can be internal or external, to carry the transfer the shear from the beams to the column. Several post-tensioned timber frame buildings have been built in New Zealand, including the recently completed Beatrice Tinsley building on the University of Canterbury campus, which is shown on the left, the Young Hunter House in the top right, and the Trimble Navigation building on the bottom right, among others. Current design practice for the design of post-tension timber structures in fire uses what's called the unprotected approach, where unprotected refers to the fact that the tendon and the anchorages are not protected from the fire. Because of this, it is assumed that the tendon and the dissipators heat up and lose all strength and stiffness, and consequently the beams are treated as simply supported. While the unprotected approach is easy to design for, the moment-resistant connections are neglected. Of the 7 post-tension timber buildings surveyed in 2013 in New Zealand, they all used the unprotected approach, where the effective sections of the beam and the column are reduced by the char depth and a zero strength layer to account for the hot wood under the char layer, and the tendon and the dissipators are neglected. There are several problems with this approach. The first is that the design and construction effort and expense of the post-tensioning system and the dissipators is wasted because they are simply neglected. Perhaps most importantly, these design methods do not actually assess how the connection will actually perform in the fire. Furthermore, only the standard fire exposure is recognized, not real fires, which have decay phases. There's no experimental basis for the performance of these connections in fire, and so the effect of detailing is unknown. Frame action is lost in the unprotected method, and so there are questions about the consequences of this on post-fire stability and the interaction between gravity and lateral systems, and the fact that damage at one connection can affect the full frame because the tendon runs the length of the frame. Post-tension timber frames are a system of heavy timber beams, columns, and connections consisting of tendons and dissipators as required. In a fire, the heavy timber beams and columns will behave as typical heavy timber members do in a fire, with a charring layer forming on the outside of the cross-section. The key to understanding the full system performance of these structures when exposed to a fire lies in understanding the connections, as these are the critical components which will govern the overall structural performance. So, if we want to be able to design our structures to perform in a real fire over the full duration of that fire, we need to understand how the connection behaves to understand how the whole frame will behave. To illustrate how different connections in timber structures perform differently to the heavy timber members themselves, we'll examine this simple case. If we take a cross-section through this beam after it has been exposed to a fire for some time, a char layer will have formed on the surface, underneath which there is a hot layer of wood, which we call the zero strength layer, because it is so hot that we consider it to have zero strength. And the remaining internal of the section is the load carrying portion of the section, known as the effective section. If we compare this to a section taken through a connection which has a steel bracket with 2 bolts here, we see that because the steel components heat up, they conduct heat deep into the inside of the connection, and they change the zero strength layer and change the effective section of the cross section at this point. And this illustrates how different the performance of timber connections is to the performance of heavy timber cross sections. So given that we need to be able to assess the full structure performance of buildings exposed to fire, of which the connections will play an important role, my research has 2 aims. The first is to investigate how post-tension timber beam column connections respond in fire, and 2, how do we design these structures efficiently for robust performance over full duration of the fire. And while my research focuses on post-tension timber buildings, the general principles will apply to all timber buildings. So since we know how these connections perform at ambient and how in general timber and steel materials respond to fire, we can come up with how we expect these connections to perform when exposed to fire. During the initial stages of the fire, the tendon force in the tendon will still be relatively high, and the decompression moment at the connection will be greater than the applied load. But as the tendon heats up and the decompression moment decreases, a gap will eventually open at the connection so that the dissipators can be utilized to provide additional moment resistance. As the tendon continues to heat up and undergo thermal elongation, the tendon force will continue to decrease, and the dissipators will heat up and lose strength and stiffness, and so larger and larger rotations will be required to maintain the load-bearing capacity of the connections. But we need to undertake some experiments to quantify all of these effects and break down the complex interactions between all of these components. So we need to undertake experiments to understand the mechanics of how these connections perform, rather than undertaking fire tests to get a fire resistance rating as traditional fire testing does. My experimental program has 7 tests in total. 2 of these tests examine connections under shear loadings. The first of these uses a steel bracket screwed to the column, while the second uses a CHS epoxied into the beam. There are 2 tests where connections are subject to moment loads. The first of these uses a CHS epoxied into the beam, and the second uses a steel bracket fixed to the column with coach screws. And then there are 3 tests that look at the same connection under the same loading, but where the fire exposure is changed, to examine whether a fast cooling phase or a slow cooling phase is more severe for timber connections. 6 of these tests use smaller wood sections, 250 millimeters by 220 millimeters for the column, and the beams are 400 millimeters deep. And one test uses almost 1-to-1 scale sized members that we see in real buildings, with a 800 millimeter deep column and a 700 millimeter deep beam. And I'll be talking in this presentation about the recent fire test that was done on that large 1-to-1 scale connection, which is this one here. One of the challenges with doing fire tests on heavy timber members is obtaining the thermal field in the timber members. To measure the temperatures, we use thermocouples, but because timber has a steep thermal gradient, we need several thermocouples at a location to capture the thermal gradient, which is quite steep because timber is a poor conductor of heat, and there is the moisture that must be driven off, which absorbs energy. So the method of how you install a thermocouple can have a big influence on the temperatures being measured. 2 of the concerns are having good thermal contact between the hot junction, which is the bead between the 2 thermocouple wires you can see there, and the wood, and that not too much heat is conducted down the thermocouple wire away from the hot junction. The other concern is knowing where these thermocouples are located in the wood. For these tests, considering the large size of the timber members, I routed small grooves in the surface of the timber laminations, and I glued the thermocouple wires into these laminations. This way I knew where the thermocouple junctions were as an alternative to drilling in the thermocouples, where with drill wander the thermocouple junction can end off target a little. The testing is conducted using the large furnace at the Building Research Association of New Zealand, or BRANZ. It's shown here undergoing its pre-burn test, where you can see some of the burners on the side of the furnace are activated. And this is basically like a really large barbecue that can heat the specimens up to over 1100 degrees. The test specimens are located on a trolley, shown here on the left, and which is then wheeled up against the furnace to form the enclosure. This sketch shows how the test assembly was configured. The column is inserted into a loading frame so that an axial load can be applied, and a point load is applied at the end of the beam so that the connection is loaded with a moment, and then there is a cabinet that is fitted around the test specimen to enclose the test specimen, and it is configured so that the beam is exposed to three sides, just like if there was a floor on top of it in a real building, and the column is exposed on all four sides below that same floor level. These two images show the connection that was tested. It utilizes a large steel bracket which was fixed with coach screws to the column, underneath which are reinforcing screws, and then there are two McAloy bars which were used as tendons, and there are SHSs that form the ducts through the column. The timber column was 800 millimeters deep by 300 millimeters wide and 3.6 meters high, and the timber beam was 700 millimeters deep and 2 meters long. This photo shows the test specimen fully assembled, and the test fitting of the cabinet which went around the beam and the column to form an enclosed furnace. This photo shows the exposed surfaces of the connection when it was put against the furnace, and then underneath the beam you can see a flap that was put in to allow downwards displacement of the beam while maintaining the integrity of the furnace enclosure. These pipes with the square plates on are plate thermocouples, and they measure the thermal exposure to the beam and the column. And this photo shows the test setup before the test is about to start. You can see the top of the column protruding out of the enclosure as well as the beam, and there's the load being applied to the end of the beam. And there were over 256 thermocouples that were used in this test, and that pushed both logging systems right to their capacities. This is a photo showing the test underway at 32 minutes through the exposure. There is two small windows that we fitted into the enclosure, one in the middle of the photo there to look up at the connection, and there's one on the right hand side of the enclosure to get an elevation view of the connection. These photos give you a sense of what the conditions are like inside the furnace. You can see the flames on the timber column here, and this is a slow motion video of what it's like inside the furnace. This is a time-lapse video of the elevation of the connection. You can see that it takes a few minutes before the timber surfaces ignite and the char surface forms. And now we begin to observe cracking of the char on the timber surfaces. and then only at the very end of the fire exposure does a gap begin to open at the connection. This footage was recorded using a GoPro in a water bath, but some of the water on the surface got quite hot. This photo shows what the connection specimen was like at the end of the test. You can see the significant downwards deflection at the end of the beam. And this is another view of the connection. These are a close-up view of the connection, and you can see the gap that has opened. You can see that charring occurred on all surfaces, and on the right-hand image at the bottom you can see how the steel plate is bearing on the reinforcing screws that were placed in the timber column. These two images show the steel bracket and then the beam end that was placed against the timber bracket. You can see the timber on the end of the beam did begin to burn, as it's all black, and those wires are thermocouples that were used to measure the interface temperatures between the steel bracket and the end of the beam. One of the interesting observations that we observed during the test was what was happening at the anchorages. This is a photo of the anchorages at the end of the test, and both anchorages started the test with the same amount of thread outside the nut as the bottom tendon. But you can see that the top tendon, as the nut and the thread got hot from the fire, that the bar actually got pulled through the nut. This figure shows the rotation of the connection during the fire exposure. It follows the expected pattern, with rotations increasing slowly during most of the fire exposure. But at the end, towards failure, the rate of rotations increase significantly. The tendons each had a load cell equipped to measure the force in the tendons. During the first 30 minutes of the fire, both tendons have a similar tendon force, but after 30 minutes, the bottom tendon decreases in force much quicker than the top tendon. And there's the plateau from about 37 minutes, which is where the pulling through of the thread on the nut occurs. So in conclusion, we've seen that understanding how connections perform in a fire is key to understanding the full structural response in a fire. We've looked at the results of a recent fire test of a post-tension timber beam column connection and observed how it responded to a fire. And we've seen through that example that the connection response in fire depends on the specific connection detailing. And we've seen that failure mechanisms in fire can be very different to those at ambient. The experimental component of my research is being undertaken at Brands because they are the only people in New Zealand with the furnace facilities for structural fire research. And I've been asked to also show you some of the other fire facilities they have there. So Brands actually have two furnaces. The large one, which I showed you earlier in my experiments, which is on the left here, which has an opening of 3 meters wide and 4 meters tall. They also have a smaller furnace, which is a little over 1 meter wide and 2 meters high, and that's good for testing smaller specimens such as doors or fire-rated penetrations. Brands also have what's called an ISO room, which is used for conducting tests according to the ISO 9705 standard, which is used for testing wall and ceiling lining materials for reaction to fire tests. In this test, all the surfaces of the room are lined with the test material, and then a small burner is placed in the corner of the room, and then the amount of energy from the fire and the combustion products released are measured. Brands also has 2 facade rigs, and these are used for conducting full-scale facade tests. This photo shows an image of one of those tests in action. There's a L-shaped piece of wall, and the facade test system is built on that, and then a wooden crib is burnt below it, and this is to test the flame spread up facade systems. Thank you very much for listening to this presentation. I'm currently in the lab completing the 7 tests. In fact, last week we just completed the 2nd test, with the 3rd one getting ready to go next week. So if you're interested in the results from all of these tests, then keep an eye out for more comprehensive results later in 2021. I'll be answering questions after the presentations. Thank you.
So tomorrow is the last of our series of the Research Showcase, and we'll be presenting the University of Queensland Fire Showcase. So hopefully you can attend that. So thank you, everyone.
Thank you. See you tomorrow.
Thanks, Kelly. Thanks, Lisa. See ya.
Thank you.